So, hello to everyone. It is nice to see you all here at the Conference for Students of Physics and Natural Sciences Open Readings 2022. I'm Lukas Neimovičius, one of the organizers of the conference, and I hope that you are all well. And I'm happy to announce that this year we have more than 450 participants from many countries worldwide. Those participants are going to share their expertise and ideas in various scientific fields during the scientific journey of 4 days. Therefore, I would like to wish you to experience the joy of new discoveries, get some new interesting ideas, and have a pleasant conference. And right now, I would like to introduce a person who will open the conference. It is the senior researcher at the Center for Physical Sciences and Technology, the associated professor at Vilnius University, as well as the winner of the National Discovery of the Year 2021. Let's welcome Dr. Renata Butkutė.
Good morning, everybody. Thank you, Lukas, for presentation, for introduction, thank you, organizers, for invitation to the opening ceremony. And good morning, young researchers. Good morning, colleagues. Good morning, ladies and gentlemen. So a year has passed, and we come to this conference again. But it's sad that the second conference is online conference, remote conference. But we can expect from this practice in remote conference that we can learn something useful for us. For example, how to share our knowledge, how to share our achievements, also how to plan our limited time in laboratories, how to communicate with our international partners. Yes, and this pandemic years made us more stronger, but maybe not so stronger as the nature wishes for us. So this year, several weeks ago, the nature tested once again us by the war in Ukraine. And this war is not only against Ukrainian people. This war is also against all people in the world, and even against a Russian scientist. And it is a punishment for Russian scientists by President of Russia and government that they can't attend this conference and share their achievements and knowledge. So my wish is to win this war by intelligence, by our intelligence and knowledge. And in this way, I wish to all attendees to share the knowledge, to discuss. I encourage to put the questions, suggestions, comments. Don't be afraid to ask, and let's win by our knowledges. I'm sure that our knowledge will help to live in future peacefully. So thank you for your attention. And one more note, I like your title of conference because the open readings invite all discuss and share the knowledge for our better life. Thank you, Lukas, and thank you for all attendees. Good luck.
So, okay, let's start our first presentation by the Luisa Torsi. Okay. Do you hear me?
Yeah, I can hear you.
Okay,
yes.
we can see you, can hear you, yeah?
Okay, now I'm sharing also my screen. You should be able to see it.
That's fine.
Shall I start? No.
Yes, sure.
Okay, wonderful. Okay, thank you so much. It's a pleasure and an honor to open this conference, and I thank all the organizers, Lucas, and all the others, and I'll definitely share the wish Renata has brought up, really let's have our intelligence and our knowledge to govern the world. That is really the major, achievement we can hope at. And definitely I share also the logo of the conference with the Ukrainian flag in the back, because we are all with the Ukrainian people right now and with all the people that are against war. I will be talking about the use of large or wide interface to detect a single molecule and to detect marker at the zeptomolar, at the tenths of zeptomolar level. Just 1 second, here we go. First things first, so here is the group. We are quite a interdisciplinary group where a lot of competences are there. So it's a group of analytical chemists, basically, and I like to bring up the name of Eleonora Macchia. She did a number of the experiments that I will be presenting, has a postdoc in my lab, and now she won an early stage year C grant, so she will be now setting her own group. And then Paolo Bollella, expert in biosensors, who just got hired in my group. But then we have Professor of Physics, Professor Gaetano Scamarcio, Professor of Physical Chemistry, Professor Gerardo Palazzo, and Professor at the University of Brescia, Electronic Engineer Fabrizio Torricelli, expert in pharmaceutical science Giuseppe Mangiatordi, and Professor of Physics Ronald Ostebacca, who is also my host at Abo Akademy, where I am adjunct professor. So what's the outlook of my talk? The outlook of my talk is as follows. Label-free single molecule detection has been so far carried out at the nanometric interface. I will show you the difference between working with a small interface and working with a millimeter wide interface while performing ultra-sensitive assays. While next generation sequencing has made possible with a commercial device to detect one single copy of a nucleic acid marker, protein detection at the single molecule level is still challenging. There is no commercial technology that allows for this. And we are developing a technology that is now quite in an advanced state, I would say, to detect single proteins in a real fluid at the tenths of zeptomolar concentration level. What we did, basically, at the basis of our technology, there is this idea of conceptualizing cells' ability to actually sense at a single chemoattractant, despite the fact that a cell surface is not a nanometric surface, is much, much larger, is micrometric surface, and the footprint of a single marker or a single protein on the cell surface, it's really negligible. Nonetheless, I'll bring up evidences of cells that are actually able to do single molecule detection under these conditions. And so by conceptualizing cell ability to detect a single molecule at a wide interface, we designed our single molecule with a large transistor device. As I anticipated, the single protein detection is still, so let's put it in a wider perspective, in a wider, on a wider background. The immunometric assays can detect a single antigen. The best that can be performed nowadays is with the Simoa planar array by Quantification that can detect in the low attomolar level, can detect a protein and an antigen in the low attomolar level. The device's label needing is rather long. It takes at least 4 hours, but sometimes even more. And it cannot reach nowadays 10 zeptomolar concentration. Nonetheless, we are talking about a very interesting technology and a very powerful assay that is now in our lab, and we use this assay to benchmark the assays that we perform also with our devices. Now, single molecule quantification is something that has a relevance also from a fundamental point of view. In fact, if you want to analyze, can you see my pointer here? Okay, very good. Not sure whether I should change it to. No, okay, that's fine. Now, when it comes to quantifying the concentration of a solution, if you want to do so, as we usually do, by assaying the concentration of a given marker in a bulk solution, maybe through the fluorescence of the molecules, you are not able to assess to quantify what is the concentration of this solution, for instance, just by measuring its fluorescence intensity. You need to compare it to a calibration curve, which clearly it's time consuming, because before any assay you need to calibrate your system. On the other hand, if you use a system capable to show you the fluorescence that comes from each and every molecule in the volume you are assaying, then you can quantify right away that here you have 1 molecule, here you have 4 molecules, here you have a higher number. And these can be done with no need of calibration curve. So, going from concentration versus counting in assessing in quantifying a solution, it's clearly an advantage in terms of time and materials you have to use in an assay. From the point of view of the applications, we can clearly see that if a clinician uses a very sensitive diagnostic tool, he will be able to come to a conclusion about the diagnosis of a given disease, a progressive one, in a much shorter time, and maybe at the stage where the symptoms are not yet there. And this basically means putting the clinicians, giving the clinicians the attack advantage over the disease, and the chance to cure the disease will be generally much higher. So the being able to detect a marker when its concentration is extremely low in body fluid, it's a great advantage. If this body fluid is also a peripheral fluid, such as blood or even saliva, clearly the advantage is even higher. So the application, the applications of an ultra-sensitive immunometric system, diagnostic system are clear. For instance, one of the technologies we are developing is an array that we are developing within the single molecule bioelectronic smart system array for clinical testing, the SIMBIT project. It's a RIA project, European project. We are coordinating with other 8 nodes all around Europe, and the model here, the system we are, the prototype we are developing, it's basically an ELISA plate, 96 well ELISA plate that is completely electronic in the reading of the immunoassay, and it can go down to single molecule detection, and it's handheld and very fast. So clearly a revolution in the world of diagnostic devices. And this is a pictorial view of the first prototype. Is a 4x4 matrix, and the features that we can already say, that device is endowed with are the following. Again, world record in protein sensitivity down to single protein in 100 microliters. It's the unique assay, the sole assay that is able to detect both amino acid and proteins. It's super fast. In half an hour, the results are ready to be processed. It's cost effective, and it can be adapted to a number of different diagnosis by just changing the antibodies that are attached to the gate of our electrodes, and is multiplexing. We can detect more than 1, up to 5 markers at the same time with the same biofluid. And this is the SIMBIT consortium at the first and only meeting we could held in person on the Garda Lake. Now, let's go back a bit to state-of-the-art now. State-of-the-art in single molecule detection, and those usually has been endowing so far mostly near-field approach. Near-field approach basically means that you have a nanometric interface that detects the single molecule that is your analyte. So you can have a single nanowire, a nanopore, or a nanogap in an electrochemical detection. These are extremely interesting and scientifically sound approaches that are able basically to work at the single molecule resolution. So you have information on each and every single molecule interaction. However, we can work at single molecular resolution, but not at single molecule detection limits, which basically means that the solutions that these approaches are able to assay are very concentrated solutions, and hence it's a conceptually or scientifically very sound approach, but is not does not bring you to work with an extremely sensitive device. In fact, when you have a nanometric interface, and this nanometric interface is functionalized with an antibody, and this is the antigen you want to detect, it can be demonstrated that the interaction, the cross-section of the interaction between the antigen and the nanometric interface is feasibly high only if the two are restrained in 1 femtoliter, so basically in a volume that has a 1 micron edge. But now 1 femtoliter is by far not a volume that you can process in a real application. In real applications, you need to have at the very lowest 10 microliters volumes, but much easier is to work with 100 microliters. So in 100 microliters, you actually have 10 to the 11 femtoliters. So your femtoliter is only a tiny part, a very, very tiny part of your wall volume. And basically, if this is your interface, nanometric interface, and these are the antigens in the 100 microliter volume, if you want to have a feasible cross-section in 10 minutes, you need to make sure that basically you have an antigen for each femtoliter of your 100 microliters. And this basically means that you are working with a nanomolar concentrated solution. And clearly there are a number of very well assessed immunometric system, ELISA in first place, that are capable to work at picomolar concentrations as limit of detection. So clearly this approach is not the right one for an assay. Basically, what the issue here is what is called the diffusion barrier issue. And now, however, it is a fact that, as I was anticipating, cell can detect and track single molecules. For instance, receptors in moth antenna can detect pheromones at the single molecule entity. Rod receptors in the retina can detect a single photon, and a sea urchin sperm can track and count a single molecule in the open sea. And now, while the trafficking in those systems are all very different, those molecules all share a common feature. They are packed with the receptors on their surface. So up to 10 to the 4th on a micrometer square. And clearly the footprint of a single molecule, and let's not even talk in the case of a photon that has no mass. We have that the target molecule, if it's a protein, it's about 1 nanometer square in footprint, while the detecting interface is about 10 to the minus 10, 10 to the minus 8 meters square. So we have up to 8 orders 8 orders of magnitude difference between the footprint of the protein that is actually impinging on a cell surface and the surface itself. So there's no way, you know, the detection is correlated to the area involved because the area is so tiny, and hence amplification process must be in place. Nonetheless, we use this approach to fabricate our devices, and we decided to work with a large area device. In this case, basically, what we have is a very large interface, not a nanometric interface. And when you have a millimetric interface in a large volume, you are actually able to detect at extremely low concentration. I will show you, we were able to detect at 10 zeptomolar. So the first thing we have to say here is that the diffusion barrier issue is not an issue anymore when you are working with a very large interface. We want first to prove this, well, first of all, we were in fact actually able to detect at the 10 zeptomolar concentration limit of detection with a large area transistor, and we were the first one to demonstrate this in 2018. Now there is another group at KAUST that was able to prove us right. And yeah, so basically the idea is that we have a 9 nanometer square antigen that detects over 10 to the power on a 1 millimeter square surface. So we have up to 10 to the 12 orders of magnitude difference between the footprint of the protein and the area of the surface, and is like a droplet falling on a pond, on a 1 kilometer large pond. So it sounds really unreasonable, but in fact is not, as I will show you. I'm trying to, okay. So first I'd like to show you how we demonstrated that the Brownian diffusion can be actually used to demonstrate that the diffusion barrier does not hold when we have 1 millimeter square wide surface. In fact, in this case is a 0.2 centimeter square surface that is packed with antibodies, and this is the antigen. Considering the drifting, the diffusion constant for an antigen, in this case is IgG that is interacting with anti-IgG. When IgG, the diffusion is for IgG is almost 10 to the minus 7 centimeter square per second, and so using the Debye constant, the Debye law here, the Einstein-Debye equation, we could say that IgG in 10 minutes spans a sphere of a 0.37 millimeter. So basically, let's say that this is the volume that is spun by IgG antigen in 10 minutes. So if we consider now the probability for an IgG to be close enough to bump into the anti-IgG, the huge number 10 to the 12 anti-IgG attached to our gate, the probability for this to occur, it's the volume of the cylinder that has a height of 2 delta r and a base, which is the round base of our gate, and so it's the volume V delta R divided by the wall volume of the assay, which is 100 microliter. Now, we can, and the F function, if we put all the constants in and the variables in, looks like this one. Now, what is the probability that at least one antigen strikes on the surface? It's captured by the surface, and the surface responds afterwards to this selective binding process. Well, the probability is the following. So it's F, which is the probability of one antigen being close enough to the surface, times the probability that a second antigen does not strike on the surface, which is 1 minus F times F. And what is the probability that if we have 3 antigens there, one strikes and the other 2 do not strike, it's clearly F times 1 minus F square, and this goes on until, if you have n particle, until 1 minus F at the power of n particles less 1 times F. Now, this is a very simple equation, and the F is the only function we are using it in, and the F function does not have any independent variables. It's all, this is the radius of the gate, this is the wall volume, this is the diffusion constant, this is the incubation time, and by using this equation, we are able to beautifully model our data. What are our data? Basically, is the normalized response of our device has a function, is the dose curve of our response has a function of the number of molecules. The red squares are the response of our transistor device, and the error bars is the replicate, is the error over 3 replicates, and this the red curve is the fitting for the 100 microliters, and the blue data are the data in 1 microliter, and clearly we can say that in the case of 100 microliters, the number of molecules at the limit of detection level is around 8. So in this case, we have a very low number of molecules that need to be there in order for have one that is actually striking and giving the response of our device. In the case of 1 milliliter, clearly we are going to we need a much larger number of molecules in order, it's 175, in order to make sure that at least one will strike against the gate. And the same function can be used also to model the normalized response as a function of the incubation time, and also in this case it is clear that we can model with the very same equation and with no independent parameter the data as a function of time. So the diffusion is not limiting our devices, and it's possible for a large interface to detect a single molecule. While again, in 2018, we were the first one to demonstrate this at the single molecule level, and I will show you data afterwards. It is known in the literature since many years that a transistor device can detect at the femtomolar level, attomolar, 100 femtomolar, femtomolar, 4 femtomolar level, with different technologies, with a transistor that exposes to the solution we want to to analyze are very large interface. But only now we are really rationalizing why. And for instance, in this case, let me show a recent examples of 2020, where the virus of COVID was detected at the attomolar level, or even this is an example of 2021, where the COVID virus was detected actually at a single molecule level. And this is basically the device we have developed in 2018 when using a transistor and a large interface, a gate interface. And the very important part is the biofunctionalization of the gate that has a chemical sum to which extremely dense layer of capturing antibodies is attached. We can independently demonstrate by surface plasmon resonance that actually we are able to attach to a centimeter square surface up to 10 to the 12 antibodies. And this is really the way we reassemble the packed surface of receptors that characterize a cell. And the way a transistor works, as most of you probably know, is by capacitive coupling a gate to an organic semiconductor, and two coupled charged double layers at the gate and at the transistor induces a channel of charges in the transistor, and hence the work function modulation of the gate can be measured as a shift in the current that flows in the channel. And this is a very sensitive way to monitor, to study and to detect a biochemical process occurring at the gate, because the biochemical process clearly impacts on the work function of the gate itself. And this is the very early data we published in 2008. I think I have to speed up a bit. So basically we measure the transfer characteristics of our device, which is the current as a function of the gate. And here you can see that at 6 zeptomolar, basically the red curve, which is underneath and you don't see it, is the baseline measured in phosphate buffer solution, while the black curve is the curve we measured in 6 zeptomolar solution. 100 microliters at 6 zeptomolar means that you have a large probability that no antigen is present in that solution, while if you proceed to 60 zeptomolar, you have 4 plus minus 2 ligands in that solution. And as you can see, we already see a shift in the current flowing in our device, showing that we are actually able to see, to detect at such extremely low concentration. And this is basically the shift in the threshold voltage of the device as a function of the concentration. Basically what happens here is that this is the a biolayer that is attached to the interface. We measure a given threshold voltage shift when the gate is functionalized. This means that basically we have a dipole where the positive pole pointing out of the surface, and when the binding, the selective binding between the antigen and the antibody layer occurs, the work function of the gate is lowered. This is mirrored by a shift in the threshold voltage and a lowering of the current, and basically means that the overall dipole moment becomes more, becomes closer to the normal, to the surface. And this is actually the relative variation of the current that is measured upon binding as a function of the ligand concentration. These are the actual data. You've already seen them when I've modeled it with the Einstein diffusion based equation. And this is so this is IgG, the sensing of IgG. Then we always have a negative control experiment. In this case, IgM, non-binding to anti-IgG, serves as the negative control experiment. The level of the noise in our assay is measured on the negative control experiment. So this is the average of the noise. The average of the noise plus three times standard deviation gives us the limit of detection that falls at between 10 and 20 zeptomolar, because this is 1 zeptomolar, this is 10, this is 100, and basically this is 1 plus minus 1 molecules. And if we zoom into the region between 0 and 15 molecules detected IgG, and this is all in phosphate buffer saline solution, you can see that we are actually able to measure at the limit of detection of one protein. We can also use an anti-IgM layer to detect IgM. And in this case, IgG will serve as a negative control experiment. And again, we are able to detect at a single molecule. We are able also to detect IgM, human IgM, in whole bovine serum. Also, in this case, we are at 15 proteins. And again, in 2018, this was clearly a world record in protein detection. And we are able now, we have used this assay to assay a number of different markers, for instance, C-reactive protein, and all those are detected at extremely low concentration. And in this case, we are detecting C-reactive protein directly in saliva, and the limit of detection is 13 plus minus 4 protein. We are able to detect the P24 protein that resides on the cap side of the HIV virus, also at the single molecule level. And in this case, we were also able to conceive a self-powered device where biofuel cells actually bias our device, and this is the single molecule device. This is the biofuel cell, and we were able to self-power the device in the 1 femtomolar detection of IgM. As I was anticipating, this platform is capable to detect both proteins and nucleic acids. In this case, we can show that we are able to detect a marker, a genomic marker for multiple sclerosis at the single copy level. And we have applied within the SIMBIT project, we are working at the early detection of pancreatic cancer. As we all know, pancreatic cancer is one of the worst one because it's silent, and the pancreas is a hidden organ. So it's usually diagnosed. The diagnosis comes usually too late, and so being able to detect markers for mucinous cysts that are on the pancreas, and to assess if they are benign or malignant. It's very important, because if they are malignant, that is a very important evidence that that cyst can turn into a tumor, and hence the curing of the tumor can start very, very early. And that's the reason why we are now monitoring in saliva and in blood KRAS, which is a nucleic acid marker for mucinous cyst, and MAC1, which is an oncoprotein, which is also considered a precursor for the pancreatic cancer. And this is the device structure we are working with. And here we go with the MAC1 and KRAS assay, both in phosphate buffer saline solution and in blood serum. And as you can see, the limit of detections are all extremely low. And now we are also working with the detection of the Xylella bacterium in olive sap. As you probably have heard, in our region, the Apulia region, there was the first reaching out of the Xylella bacterium, and that is devastating our beautiful olive trees. So there is a major, effort towards early detection. I mean, curing, but also early detection. And very interesting. Well, again, we are down to one limit of detection, one bacterium limit of detection, and very interesting. If you compare the calibration curve with our CMOT technology and the calibration curve you can have with the golden standard for bacteria and virus assay, the real time PCR, you can see that we are one order of magnitude lower in the detection of Xylella with our technology. And we are also now working on the detection of COVID virus, and we have a technology that is able to detect one single virus in 100 microliter in 20 minutes, so with a handheld device. What is the mechanism by which we are able to detect at such low concentration? And I'm going towards the conclusions here. Well, we are still working to independently assess with an experiment the working mechanism of our system. But the idea is the following. We have chemical sum that basically is attached to the gate. Here we have basically an hydrogen bonding system that is present all over the surface. So basically what we think there, and we have a model that shows that this might be the right track here, is that this hydrogen bonding system generates a collaborative effect that acts as an amplifier to the single binding event. Basically, the idea is the following. This is the chemical sum we have on our gate, and this is the biosum. This is the hydrogen bonding that connects the self-assembled monolayer chains on our electrode. Now, this is basically a molecular simulation of the hydrogen bondings on our electrode in the electric field, because clearly we are working in an electric field, and the electric field basically imposes an further order to a system that is already rather ordered, but those dipoles align basically in the electric field that we use to stabilize our electrode and to measure the IV curves. And so this is how they would look like, the hydrogen bonding system would look like in an electric field. Now, the idea is that what if we consider the selective binding occurring on one of those molecules, so in a very small region, and what if this affects a very limited number of hydrogen bondings there, generating a defect in a otherwise rather ordered system? And this is what the molecular dynamics calculation shows us. Basically, the landscape of the dipole's orientation on the surface changes completely if the defect is, even if the defect is restrained to a very small area of the system. And if the dipole moment orientation changes, this means that the work function change, and this impacts the transistor current, as we have seen. We have also model this on a much wider, this is almost 1,000 dipole moments. And again, even if we restrain the defect to this small area, the whole area we are modeling, the landscape of the dipole orientation in the whole area changes completely. This is just an enlarged view on how the system changes here. So it's like a domino effect. We have our tile here, antigen strikes just one of the domino tiles. It fell off. Since they are very close, in falling off, basically it affects, it makes the other falling, and in a domino effect, you have in no time, all of them will be will have changed their conformation level. They will be no more up but down. And while this model here is possible because of the gravity force, in our case, the fuel is likely the electrostatic field that we use to operate our device. So basically, the idea is this one. We have a single antigen in a layer of trillions of them. This is affected by a single binding event, a selective binding event. A conformational change takes place, generating a surplus of energy. For instance, in this area, in the case of an IgG binding to an anti-IgG, but this is an allosteric process, has many other selective immunometric interaction, and hence the energy can be shifted, moved towards the gate electrode, and here it can directly affect the dipole moment of the chemical sum, and so the hydrogen bonding system, and hence the dipole moment on the surface shifts from this one to this one. But this is not just affecting the single antigen there, but because of a propagation effect due to the presence of many hydrogen bondings, in the electric field, this expands over a much larger area, making, amplifying the response and making the system detectable. So to conclude, we are able to propose a system that sensing diagnostic system that complies with all the requests the World Health Organization has given as important for a point of care device, and although it's like a single drop falling on a lake or on a 1 kilometer wide pond, we are able to detect. We like to acknowledge all the sources of finances and you for your kind attention.
Thank you for your presentation. We still have some time for our questions.
Mm-hmm. Good.
So, do we have any? Okay, I can't see that. Okay, I can actually start.
I have one.
Okay.
Yeah, thank you. It was a very nice presentation. And my question was if the system is somehow reusable, or can it be refurbished, or you after a single detection you have to throw it away?
Thank you for your question. Basically, there is a trade-off. Detection is highly specific when it's highly irreversible. So in a biochemical reaction, you never have, it never goes back, because the high reversibility means also a high stability for the new system, which means also, again, extremely high selectivity and even specificity. So whatever kind of biochemical system you are using for detection, they are none of this, starting from Simoa, next generation sequencing, and many other, none of this is reusable.
Mm-hmm. But compared to like other detection systems, it's still relatively cheap to produce.
It is. It's extremely cheap. It's extremely cheap. We think that basically we are now developing a system that basically is like a strip test. So it's like the strip test you buy in a pharmacy and you test COVID. But the important thing is that while it's a antigenic sort of test, it has the performance level of a molecular test. So it's cheap, it's fast, and is also extremely performing, as it can detect one single virus in 100 microliters.
It's very nice. Okay, thank you.
Welcome.
Okay, maybe I can ask a question.
Please.
You showed us some, basically, the detection you are making there. You are measuring shift of threshold voltage in FETs.
Yes.
And most of your results being shown on PHT, polyhexyl field. So do you have, when you put the saliva or blood on transistor with an organic layer, do you have some issues with stability of or degradation of that layer itself?
Yeah, I had no time to go into all these details, but we have an extremely sophisticated while easy and fast protocol we comply with. Basically, what we do is that only the gate, the sensing gate, is actually incubated into the high ionic strength and very messy fluid we want to analyze. Then the gate is taken off after 10 minutes, is washed, and it's put into the well, the measuring well, and the measuring well, it contains only deionized water, so the transistor never sees anything else than pure deionized water. And so, and all the stability issue has been studied thoroughly. We have published a number of papers, and now we have a protocol of stabilization of our device that takes 5 minutes, and it's extremely reliable.
Thank you.
Okay.
Okay, so do we have any other questions? Okay. Well, I can ask another question then. So basically in FETs, when you put some on a gate, it's also have an impact on the conductivity of the layer itself, probably. And so my question is, do you really need the gates? Maybe it's easier to measure the conductivity between two planar contacts. So I understand that putting the gates, you're probably increasing the sensitivity. But
okay, so
how much
first of all,
increasing?
yeah, I fully get your question, and thanks a lot. It's a very fundamental one. So we have two reasons to use a transistor. First one, capacitive coupling adds up to a factor of 1,000 in sensitivity. So you have an amplification that is typical of a transistor configuration. We need 10 to the 12, so it's an amplification, but we need a second amplification, which is much, much more powerful. But anyhow, the transistors allows you to get access to a further amplification factor of 10 to the 3. Having said that, the major reason why you want to use a transistor is that you want to decouple completely what happens on the channel and what happens on the gate. Because if you would sense only with a resistor your system, you would have to functionalize your channel. And functionalizing your channel, whatever material you use, from graphene to whatever else, means basically you are affecting the delocalization of your charge transport right where you have your channel. So basically, you are messing up the mobility of your channel material in order to attach a sensing layer, capturing layer. A second and maybe even more stringent fact is that if you want to use a resistor, you would have to put your whole device, even through a microfluidics or whatever, in contact with the messy fluid you want to analyze, and washing that and getting rid of a non-specific binding is a nightmare. So at the end, we have evaluated this very closely because it would simplify a lot the system, and we have even tried it, but it's not working at all.
Okay, thank you. Do we have more questions? No, we still have maybe time for one or two.
Yeah, I think we have a couple. Hello, presentation.
We still have something on the chat, but basically it's just there is.
Hello, the presentation was very interesting. I'm at work. I cannot engage listening. Okay, no, I don't see any question here.
I don't see anyone. Okay, if no questions, thank you for a presentation. It was
welcome.
Nice and thank you. So
thank you so much. Bye, bye. Thank you. Bye.
Bye. So this is the end of this beginning of this session, right? So that's it. So I think next session starts then after 15 minutes.
Yeah, 10, 15. Yeah. Thank you.